Well, we've got a real special treat for you tonight. We're going to tackle a whole bunch of monster integral review tonight. We're going to go back and kind of take a journey through all the integrals we've seen since day one, since we first introduced you to this great symbol. And I want to ask you, when you see this symbol, is this how excited you get? Is that the amount of determination you attack these problems with? Absolutely love this picture. Can't say enough good things about the picture and the passion that is displayed. I recently heard a coach talking not too long ago about a very special acronym. And that acronym goes like this. Gotta get there we go. EUHK. Enthusiasm unknown to humankind. And that's the kind of passion that I want to see you walk in with tomorrow, ready to tackle these bears, ready to get after them. So without further ado, let's go ahead and get started. I'm sure you've all seen this very, very poetic saying here. It says, a journey of 1,000 miles begins with a single step. And it's such a simple phrase. And I think because it is so simple, it makes it easy to dismiss it. But very profound statement, and I think it certainly applies to what we're doing. You know, when you think about tackling this gigantic mountain that we call AP Calculus BC, it's very easy to get overwhelmed. But you look back at what you've accomplished so far and how you've gotten to the point you're at now. And it just started with a single step. It just started with one single day, learning one very simple concept, and you put them all together, and it makes for quite a magical ride. And that's all we're going to do tonight. We're going to kind of hit the pause button, so to speak. We're not going to tackle a new topic, and we're just going to kind of go down memory lane, as we said. And we're going to revisit, a lot of the things we've hit over the past month and a half. Well, one of the reasons I love all the integrals is that it's very easy to check your answers. Relatively speaking, all we're going to do is simply derive the answer we get when we're all done. And when we derive that answer, if it matches the original problem, then we know we're in business. We know we did something very, very good. The other option is, when you're dealing with a multiple choice question and they want you to integrate yada, 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 a lot of times, it is more efficient to just integrate what they've given us with a U sub or something. But I've seen moments, and I've seen students who are really successful at this trick, where they would just take, each multiple choice and just simply start deriving each choice until they got a match with the given problem. And there are pros and cons to that, especially if you start with A and you go single one at a time and the answer isn't until E, maybe you've wasted a lot of time. But you might get lucky if the right answer is A and that's the first one you drive and you got a match, then by golly, more power to you. Now, believe it or not, the first integral that I ever introduced you to was in Good Morning Math, and we introduced you to a definite integral that could only be done geometrically. Okay, such as the absolute value of 3x minus 1. And so we're looking for the area underneath the curve there. And I shouldn't say it's impossible to do it algebraically. There certainly is possible. You just have to rewrite the absolute value function as a piecewise function and then, set up two integrals to do it. But I think it's so much more time consuming. And so I've really just preached, we're going to take only a geometric approach. And what you're going to do is you're going to set that function equal to 0. And what that's going to do is that's going to tell you where the vertex lies or where the x-intercept is. So if that's x equals 1 and that's x equals 2, then by golly, we've got ourselves a vertex right there at positive 1/3. And we want to integrate that rascal from 0 up until x equals 2. So what we've done is we've created two triangles, one very tiny rascal, one very large one. I'm going to find the area of each triangle and then add them together. If you want the height right here when x equals 0, you simply plug a 0 into that function, and you're going to get a height of 1 unit. And then again, over here, let's plug 2 into that function, and it looks like we're going to get a height of 5. So the height there is 5. My base here from here to here is 1/3, and my base from here to here is going to be about 5/3, I believe. So hopefully my number crunching's up to par here. We'll go ahead. The area of the first triangle, we got 1/2 times its base times its height, plus 1/2 base is 5/3, height is 5, and let's see, so 1/6 plus 25/6 for a grand total of 26/6. So basically we are going to see a couple tomorrow where they're geometric only. Another example of one that's geometric only that we haven't seen in a long, long time would be the semicircle. Maybe a semicircle with a radius of 5 units. They may ask us to integrate from -5 to 5 or just 0 to 5, something like that. Well, for the rest of tonight's video, we're only going to be working with indefinite integrals just to kind of save some time. I feel pretty confident that we can use that first fundamental theorem to evaluate the definite integrals. And one of the first things I'm going to say on a lot of these things that we review tonight is you got to know the rules, right? If we don't know what the power rule is, generically speaking, then we're in a world of trouble. So if we're just integrating x to the nth power with respect to x, and there is that one disclaimer that n is not allowed to equal what? Do you remember? -1. Then the antiderivative is going to be x raised to the n plus 1 power divided by the new exponent plus c. A lot of times we don't necessarily divide by the new exponent. We're more likely to multiply by the reciprocal of that new exponent. So a couple of examples that we could look at here is, we're going to try to incorporate a few extra tricks just to brush off some rust here. So that's x to the 4th minus 4x squared plus 1 all over x squared. And the trick here, of course, is we're going to make like a beaver and split this bear up. And that's viable anytime your denominator is a what? Yeah, monomial. All right, so divide the first term by x squared, you get x squared, and then minus 4, and then plus 1 over x squared. And I'm going to write that as x to the -2. Always like to rewrite it with a negative exponent, unless it is, of course, -1, and then I'll leave it as a fraction. We're going to get 1/3 x cubed, and hopefully this is a real walk in the park for you. If you're breaking a sweat at this point, we're probably in trouble, and we really need to do a new crash course on these. One other one with the power rule that I want to throw out there. This showed up on a recent quiz here, and we had a little trouble rewriting something like this. So I want to talk about, as we rewrite this rascal, the coefficient is 1/4, okay, as opposed to just 4. And then we've got x to the -1/3. Certainly haven't done any calculus yet. Now I'm going to add 1 to that exponent. It's now 2/3. And I'm going to multiply by his reciprocal, which is 3/2. So I'm getting 3/8 as my new coefficient plus c, and we're good to go. Well, after the power rule, the next thing we introduced you to is what we like to affectionately refer to as the Big Six trig rules. And basically what they are is they're married directly to the 6 basic trig derivatives we learned a long, long time ago. And as long as you knew those derivatives down cold, then these 6 antiderivatives were a walk in the park. And I'm telling you, and from this point forward, we really don't have any excuses on why we wouldn't know these. If we have to, we may just have to make some flashcards and, pull them out from time to time to brush up and refresh. But, as far as these big 6 go, again, just you could always take the derivative of your answer to check your work, but the antiderivative of sine is going to be negative cosine. Remember back in the day we said the derivative of every trig function that begins with the letter c throws us a negative. Now it's just the opposite is true. So we integrate cosine and we get positive sine x plus c. The antiderivative of secant squared is, of course, tangent x. And the antiderivative of secant tangent is secant. Whoops, goodness gracious. My stylus pen is fading on me here. I'll try to fight through it here. Alright, I think we got it in there. Secant of x plus c. The antiderivative of cosecant squared is, just ask yourself, who did I derive to get an answer of cosecant squared? And we're actually going to derive negative cotangent to get a positive cosecant. And then last but not least, we're going to say negative cosecant of x. If I derived that, I would end up with a positive cosecant cotangent. Now, when it comes to integrating these functions, probably the most creative they're going to get, and we saw one really, really good worksheet a while ago that, really jumbled up the trig functions. And here's one example how they might ask us to get a little creative. I could rewrite this one fraction as the product of 2 smaller ones. I could say sine over cosine times 1 over cosine. That's certainly equivalent. And then we could rewrite these. We could say, well, this is really tangent times secant. And then it fits one of our big 6 rules perfectly, and his antiderivative is just secant of x plus c. Well, then we kind of rocked everybody's world by introducing you to some u sub, and the first night we did u sub, we just preached, letting u equal the inner function. Now, this is kind of a good moment to kind of generalize and throw out some tidbits about u sub. we have these rules, we have these guidelines, so to speak, on what to let u equal, but there really are no hard rules. I might tell you, we're going to let u equal the denominator 90% of the time, or we're going to let u equal the exponent 80% of the time, but these are just guidelines. Ultimately, when it comes to picking your u, it's more of an art and a feel, and being able to visualize, what would if I let u equal this, then my du is going to be that, and it's going to cancel all the x's out, yada yada yada. So let's just take a look at one very nice example here. Let's consider x squared divided by radical x cubed plus 3. And ultimately, when it comes down to a lot of these u sub functions, it's about getting the right coefficient when you're all done. All right, we got the 3 in there. So you're looking at this, and I wouldn't let u equal the entire denominator. I would just let it equal the inner function. So as I let u equal x cubed plus 3, and I have seen some quote-unquote bad habits creeping in lately when I've been reading your test corrections and your quiz corrections, and we've just been getting a little sloppy. And so I think tonight's really a good night to just kind of get back to basics and refocus our efforts a little bit. So we're going to solve for dx. So remember, after we calculate the du, we're always going to solve for dx. And now we're going to substitute back in here, and we're going to say, well, I've got x squared all over radical u, and then I've got du all over 3x squared. And we're canceled the x squareds, and that's a good thing. We have to make sure that we've canceled all of the x's at this point, and then we're just going to pull out our coefficient. We've got 1/3. I'm going to rewrite my u with a negative exponent. Of course, if it was du over a u by itself, then that would be a totally different story. Now we're going to use my power rule, positive 1/2 multiplied by 2, so we got 2/3 plus c, and then we're just going to rewrite everything in terms of x. So we've got 2/3 radical x cubed plus 3 plus c, bada boom, bada bang, there it is. Now another really fun one, there were times where not all of the x's were able to be killed, which was always our goal with the u sub. We had to rewrite the entire problem completely 100% in terms of u. So I would start off with the inner function, of course, and this one's kind of exciting because du equals dx, and then there's no coefficient to worry about. So we come on back and we say, well, we got x, and we got radical u, and we got du, and then all of a sudden everything comes to a screeching halt because of this darn x right here. All right? So what I had to do is I had to go back to this statement, and I say, well, if I solve it for x, then x is really equal to u minus 4, and then I would make that substitution so that everything is truly, truly in terms of u. And then here's what happened. We'd get u minus 4 times radical u times du, and now you're able to distribute. Do you agree how we are allowed to distribute this term, but back earlier when everything was in terms of x, we are not allowed, okay? We are not allowed to distribute that x into the radical, and that's what was keeping us back there. So now we've got u to the, going to add those exponents, get u to the 3/2 minus 4u to the 1/2 du, and u to the 5/2 times 2/5. Let's see, u to the 3/2 and multiply by 2/3, so now I've got 8/3. And last but not least, we just need to rewrite everything in terms of x. And I'll tell you what, I think it's really time for me to go out and buy a new stylus pen. Whoops. Not you ding-dong. It's got to be x plus 4 to the 5/2 minus 8/3 x plus 4 to the 3/2. Okay, so there's everything in terms of x. Well, then a few days later, we did some more u sub, and we said, you know what? If you're ever integrating a fraction, then we're going to start off by letting u equal the denominator. And we said, that's not going to work every single time, but it's a really, really good place to start. And so look at this first example we've got. It's a very obnoxious one. We'll go e to the 2x minus e to the negative 2x, all divided by e to the 2x plus e to the negative 2x. So we're integrating a fraction, and our first thought is to let u equal the denominator. All right? And look at this is such a crazy looking problem. And just a quick tidbit, you really shouldn't have to do too much work to calculate your du. If you have to do too much work, if you're doing product rule or some crazy chain rule, then there's probably a pretty good sign that you're doing it wrong. And then I'm just going to divide that entire quantity over to here, and we'll go ahead and make that substitution here. Alright, so let's get everything in terms of u here. So we got e to the 2x minus e to the negative 2x all over my u times my du. Now what I've got to do is I've got to pull out a GCF of 2. It's very important that we see the GCF being pulled out so that we can make a nice smooth cancellation. Alright, let's pull out the coefficient so it doesn't get lost. Okay, we don't want to lose it. You know, there's a lot of clutter going on here. And all of a sudden, we've got 1/2. I'll just clean this up a little bit. It's du over u. This is the one and only time where we do not rewrite it with a negative exponent. We do not write it like this. Okay? Not in a million years. So this is just simply the perfect form for natural log of u. And I'm going to go ahead and substitute in terms of x. And I'm going to get e to the 2x plus e to the negative 2x as my u plus c. And boom, there it is. And then we moved on to another day. We said, you know, there's this really nice integral e to the u du equals simply e to the u plus c. And so I'm going to let u equal the exponent whenever I see an e in my integrand. And again, this isn't something that's true 100% of the time. It's just kind of a rough guideline to kind of get us started. So the best example that I could think of here that I thought would be productive tonight is e to the 1 divided by x power all over x squared. I think this can sometimes be a challenging one. And so as soon as you see the e here in your integrand, you know, I think we should at least entertain the thought, the possibility of letting u equal the exponent, which is really x to the negative 1. And we're going to derive that and say negative x to the negative 2 dx. Now as I solve for dx, you know, you're really dividing this term over, but I think it's better if we rewrite it one more time and we just say negative x squared times du equals dx. Alright, let's go back. We'll put everything in terms of in our integral here. So we've got e to the u all divided by x squared times negative x squared times du. If you want to put it over 1, more power to you. Cancel those. And then again, pull out the negative, and the integral of e to the u du is simply going to be e to the u plus c. Alright, now, just recently we went over those arc-trig rules, and the bottom line is, these can be slightly goofy sometimes, but the bottom line is we got to know these two rules. If we don't know these two rules inside and out, then we've got a 0% chance of getting these right on a real problem. So, for arc sine, there is no coefficient, at least one that's built in prematurely anyway. So arc sine of u over a plus c. And of course, that's just, you know, you see the radical, you see the minus sign, you start to think of arc sine. And then when you don't see a radical and you see the plus sign, now you're starting to think arctan. It does have that pre-built coefficient, and we've got arctangent or inverse tan of u over a plus c. All right, let's go try one. I'm going to show you one of my favorite problems of all time. I think this is a really, really creative problem. I loved this one. So we're going 1 over e to the 2x plus e to the negative 2x. And you first look at this problem, you think of all the things that are going through your mind. You know, oh, should I let u equal the denominator, or should I let u equal the exponent? What should I let it equal? What should I let it equal? Well, first thing I want you to do is just rewrite that very last term in terms of a little itty-bitty miniature fraction. Alright, so it's 1 over e to the 2x. And the reason I'm doing that is because the exponent right here was negative, so I just rewrote it as a fraction. Now what I've created is a complex fraction. And I've got my one big major fraction, and within that I've got my minor fraction. So what I'm going to do is I'm going to multiply, just like I would any other complex fraction, I'm going to multiply every term by e to the 2x to kind of clean up that complex part. So I get e to the 2x on top, I'm going to get e to the 4x right here, and then I'm going to get plus 1 right here. And believe it or not, this fits the arctangent mold perfectly. Alright, and arctangent is going to be something that continues to show up a whole lot as we move forward into the BC only material, this arctan rule. So the question becomes, well, if this is my a squared, then this over here must be my u squared. So ask yourself, what's getting squared to produce e to the 4x? Alright, I'm going to let a equal 1, of course. I'm going to let u equal e to the 2x, because that's what's getting squared to make 4x. And my du is then going to be 2e to the 2x, alright, which I'm then going to divide over. And now we're going to rewrite our integral. So I've got e to the 2x all over u squared plus a squared times du over 2e to the 2x. Do you see the beautiful cancellation here? Then we're going to pull out our coefficient, and everything's falling into place so nicely. I'm going to say I've got my 1/2, and now I'm going to refer back to my rule. 1 over a, well, that's just 1. That's nice. Arctan, oh goodness. Let's see, arctangent of u over a plus c. Boom, there it is. Well, we've really only got 2 rules left, and these are the 2 BC only rules. And when it comes to integration by parts, we just got to know the rule, basically. If you're integrating u dv, it's going to be u times v minus the integral of v times du. If I know I've said it before, I'm just going to comment on it again. I want you to be very crisp with your v's so that your v's don't accidentally look like u's. We don't want to make any careless mistakes halfway through the problem. Remember, you always start off by picking your u, and you're going to use the acronym LIATE, logs, inverse trig functions, algebraic functions, then regular trig functions, and then you finish with exponentials. Exponentials are your last resort for u. And then, of course, whatever's left over within the original problem is your dv. You're going to integrate the dv to get v, you're going to derive the u to get du, and so forth, and you're off and running to the races. And then, of course, there is our favorite shortcut, tic-tac-toe. And you always start plus, minus, plus, etc. U has to be something that derives to 0, and then dv has to be something that easily integrates, and then you're off and running. And I would say tic-tac-toe works, more than 50-50, probably close to 75% of the time on the AP exam. And our very last BC only topic with regards to basic integration here is partial fractions. So again, it's BC only topic. Again, we've been very, very successful at these. It's kind of like last resort. I'm going to be, partial fractions is not something that I go into a problem expecting. I think after you've done enough of these, you develop kind of an eye for them. You can kind of sniff them out, so to speak. But the bottom line is, none of your basic U subs work. None of the other tricks work. And as a last resort, we're going to rely on partial fractions. We want to make sure we get those denominators factored as completely as possible. And they're going to turn into distinct linear denominators, distinct factors, as we like to call them. And, I don't even know what's in the numerator, blah, blah, blah. And so what we're going to do is we're going to set that equal. We're going to try to rewrite it as the sum of 2 simpler fractions. Capital A over the first denominator. Capital B is another constant over the second denominator. Remember, your numerator is going to always be 1 degree less than your denominator. If for some reason we had a quadratic down here, we would then write a generic linear up here and so forth. But, that's the name of the game. We're very good at them. We'll continue to practice a little tomorrow. So hope you're feeling pretty confident. Let's walk into the classroom tomorrow expecting great things to happen, and we'll rock and roll from there.